Today, I want to go through something that is pretty close to my heart, which is bringing in some cool software tools into the world of hardware development. So we will be going through Git and GitHub and see how we can use it in the context of a hardware project using a KiCad project as well as some Arduino firmware files. And we will be exploring about 6 Git features. They are Git commit, Git branch, Git log, Git submodules, Git tags, and Git hooks. And finally, end the video with a slight discussion on the concept of semantic versioning. So for those of you who have already used Git in the domain of software will know that it is pretty used in the software world. However, in the hardware world, it is being used only recently. But there are some serious efforts going on. For example, in Altium Designer, it is backed by Git. In fact, the entire idea of using Git in Altium Designer is to make a user interface that is easy and intuitive to operate. There is also another young company, startup, AllSpice, that is also trying to use Git as a workflow for hardware. In fact, if we look at their vote for your new feature, you will see some usefulness of using such a version control. For example, for visual diff tool, for automating releases to manufacturing, for insights on bill of materials, and many other cool reasons. So throughout the video, if you have already used Git before, you'll get a sense that Git for hardware is still a little kludgy given the current set of tools and applications, but I decided to do this video because I see the trends and the desires of the hardware developers in the right direction, and I'm quite excited about it. So I hope using this video, more hardware developers who are aware of Git will start using it, and with the intention that we can all use Git and make the tooling a lot better. So let's jump right in and explore how to use Git and GitHub in the context of a hardware project. Alright, so let's start with a very simple KiCad project which has just the schematics. And then we will use commands such as git init and git commit before pushing the project to a remote new repository in GitHub. So this is the simple project that I have, and seems like the ERC is all good. And if you come to the folder structure, this is how it looks like. Inside hardware, I have the KiCad files. Now this is a normal folder in our laptop. In order to change it into a Git folder, all we need to do is git init. Now if you do git status, you see that it has detected the hardware folder, but let's do git status -u. And then you see that it is detecting that these are the 4 new files. Now, if you are wondering what are these file formats, we can refer to the KiCad's file formats, and you will see many of the formats such as KiCad PCB or .sch, which is the schematic file. But we also saw some stuff like -cache as well as .bak, which is basically the backup of the schematic file, which we typically don't want to include in our Git repository. And thankfully, Git has something called gitignore, and GitHub has its official KiCad.gitignore sample file. And here you can see many of these files are also included. So I tell you what, I am going to copy all these formats, maybe not the last exported BOM files, all these formats, and we'll include it in a new gitignore file. And inside the file gitignore, I'm just going to copy and paste the GitHub sample file. And after that, if we do git status, we will notice that a new file is created, the hardware folder. Let me do git status -u. And here you see the back file is not there. So let me include -cache as well, something like this. So usually I have an alias gs, which is basically git status untracked file. So I'm just going to run that. And yep, finally we have all the necessary files that we actually want to commit, even though our folder structure, our file structure is including the cache and the back files. So now happily I can do git add dot, which is add everything, and git commit -m for message. I'm just going to say first commit. So let me create a new repository. I'll just call it a LoRa comms, LoRa communication with an e-ink, and let it be public, create repository. So here there are instructions. We have already done the first commit. So I'm just going to add the remote URL and then git git push origin master. So upon refresh, you will see that I am now having exactly the same folder structure, including inside the hardware, I have both the project folder and the schematic folder. Actually, yep, I should add a readme. So let me go here and create a readme.md and then just say Laura comps. Now the power of Git is also in tracking the versions, and one of the important thing is the commit messages so that we know what changed and why it changed. So I like to follow this thing called conventional commits, where the commit messages follow this style. I typically have another alias to git add and git commit. So I'm gonna git commit and follow the conventional commit format, and in this case just say add readme, and let's do git push. And when we refresh GitHub, we will also be able to see the readme.md file with our last commit message 18 seconds ago. So let's try to do some changes to our schematic and see how the files perform. So I'm just going to delete this bat, which is a signal just hanging there, and I'm also going to delete this open solder jumper and just connect it via the wire. And now when I come to do git status, it will say that this file has been modified. Now, unlike a code file, viewing this .sch file is possible because it is, after all, still ASCII. I guess that's how KiCad built it. And we can even see the diffs. If I expand it, it will say, yeah, I did delete a solder jumper, or I did delete a wire as well as the text label bat. But I don't think this file format is in any kind of standard that allows us to edit it and then view it visually. But like I said, there are efforts being done in the direction that Git should be used. For example, in this talk, the speaker describes about a visual tool based out of Git, and he even open sourced his entire framework where you can also create schematics in PDF, SVG, BOM, as well as interactive HTML BOM files, and many other cool stuff. There is also this cool project called Skiddle. Skiddle has a way of describing the schematic in the format of code so that when you edit the code, it will appear visually in the schematic. But as of now, I guess you can't do that with KiCad, but you can try Skiddle. So once again, git status shows that I have changed the schematic indeed. So I'm do a git commit and just say fix remove bat net label and open solder jumper and git push it. So one of the big advantages of using a version control like Git is that we can actually step through and even go back in history and look at the exact version, open up the files, view our schematic or our PCB layout or even code. We can do this with the command git log, where we will be able to see our changes beautifully, and thankfully if our commit messages were descriptive, we will also be able to know why and how we change them. So there's this command called git log, and here you can once again see the commit. This is the SHA-1 commit, and you'll also see the author and the time and the commit message. But git log has a lot of features, and I have probably edited and made my own. You can do the same, where git log will do a graph, it will decorate, it will add a date, it will add some color format. So let's see how this git log command that I made looks like as opposed to just git log. So I just do GL, and this is how it looks like, just 3 commits. So now the cool thing is, let's say you want to go back to the commit before we removed the bat net label and the solder jumper. So we can just copy this SHA-1, come to the master branch, and then do git checkout and paste the SHA-1. So you can see it has changed to this SHA commit. Let's open the project folder and even the schematic, and if we zoom in, we will be able to see the stranded net label or the solder jumper. And of course, from here, if we want to go back to the head, just say git checkout master. And the head position was at this, and now it's switched to branch master. Now the cool thing is we can look inside the .git folder that is created, and here we can actually explore through the various files, even though it might look a little daunting. For example, under refs, you see the main or the master branch SHA-1 commit, And if you go to the log folder, under head, we will be able to see all the SHA-1 commits and the details of it, including the commit messages. So everything related to do our project resides in this .git folder. If you come to the config file, you will also see that my GitHub URL is there, as well as some configuration which we can change. Okay, so the next cool feature is Git submodules, and I use this whenever I need to share schematic symbols or footprints across various projects. And using Git submodules allows us to separate the different Git repositories of the project as well as the library. So I have a completely separate Git repository where I store the KiCad footprints, the symbols, as well as the 3D models. So let me copy the SSH URL and let's revisit the folder structure quickly. So inside hardware, I have the KiCad files. So now what I can do is git submodule, add, and then the URL that I copied, and then the file path. So usually I keep it under a folder called library inside hardware. So let's press enter and see what's happening. So you see it's cloning the entire Git repository into my current project. And now when we want to look at the folder structure, we see that it does have a library with the folder structure, which is exactly the same as what I have on GitHub. So it basically cloned this entire project. Now, if we do git status, we will see that yes, the new folder is created, but there is also a file called git modules. And inside git modules, you will see that the path and the URL has been added for the submodule. So yep, I am pretty happy that the library has been added as well as the git modules. So why don't I commit? And maybe this is a chore, I don't know. Add library as a submodule. And let me git push it to GitHub. Now, let's say for some reason we have made a change to this library. So why don't we change something really simple? Let's say this URL, instead of the HTTP URL, we'll change it to SSH URL. So in my computer, I can go to the same folder and let's change the README file. And yep, I will change it to the SSH URL. And inside the KiCad library, instead of the project library, I will once again commit it and then say fix, add the SSH URL. So I have git pushed a new change to the library folder, or rather the library repository. And now when I refresh the library repository, we see that it was changed about 16 seconds ago. So now when we come back to the project git repository, we can acquire the new library by simply doing git submodule --update, just update --remote, and then you can pass in the folder structure. And immediately you will see that my latest version of the library has been downloaded, including the SHA-1, which is like 4D18, which is exactly the same as the SHA-1 commit shown on GitHub. So of course, this will mean that the library has been changed, and then they will show you that, well, some files have been modified. So why don't we add a chore and say update git submodule for KiCad libraries and git push to GitHub. Okay, so now comes the fun part, which is at the heart of using a version control, collaboration. So let's just pretend that for this hardware project, we will have the electrical engineer come in and add a component to the schematic, while at the same time, the firmware engineer will also add in the firmware code, and later they will merge the code together. So in Git, we can create a Git branch by simply saying Git branch and then the branch name. So here we'll say add e-ink as a feature, which the electrical engineer will add. And now if we do simply Git branch, we will see that there are two branches. But we have to check out to this branch. So we'll say git checkout and then feature add e-ink, the branch name. So now you see we are working on the new feature branch. Now you see we will be acquiring a new symbol, and that will come from the KiCad library that we acquired as part of the Git submodule. So I'm going to add the path by clicking on this folder symbol, and I'm going to add the wave share e-ink module. Right, let's click OK. And now when we do git status, we will see that a new file is created. And if you want to read what's inside the file, once again, the file is in ASCII. We are able to read and somewhat deduce what it is trying to do as according to what we did visually through the user interface. But I doubt we can edit it. I mean, we can, but it will be probably highly error prone. So now our schematic does not have the symbol integrated. So the electrical engineer will now integrate the new symbol to this schematic. And there you see magically the new symbol appears. Well, let's just pretend that it has been integrated. And the ERC is also passing. Git status once again tells us that we have changed the schematic and the symbol library table. So why don't we add it as a feature, add e-ink to the schematics. So now when we do a git log, you see nothing much is shown, but you will see that it has branched off from the master branch into the feature branch. So let's pretend at the same time in the master branch. So I will be switching to the master branch and let's for fun just list the hardware. Here you will see that the symbol library is not available. So once again, the master branch has no information or changes from the feature branch. So here in the master branch, the firmware engineer will now add in the firmware code. Well, so the firmware engineer will simply create a firmware folder, and inside firmware.ino, I'll just paste a bunch of code that's something to do with only the LoRa, because this firmware engineer is not aware about the e-ink module at all. And of course, some makefile where we will do the linting, the compiling, and the uploading, and some cleaning up of the build files. So now when I do a git status, you see that 2 files are created, which is correct, by the firmware engineer. And the firmware engineer is going to add all the files and git commit -m and write a message called add firmware for the LoRa comms. So let's look at the git log now. And here you will clearly start to see the diverging branches. One is the master branch, the other one is the feature branch. Now, often a question is it better to merge often or merge a bit later, only after lots of feature changes have been done? Well, it depends on the project, it depends on the team and the convention, but I prefer the way of merging often into the main branch. So now from the master branch, the hardware engineer will merge the feature branch by just saying git merge and the branch name. So here you can write a commit message. I think I'll leave it as default, but of course you can change it too. And yep, the schematic and the symbol library table have been added to the master branch. And if we now go to the git log, you will see this little curved out and then coming in and merging into the master branch. And thankfully, because these 2 engineers were not working on the same file, there were no merge conflicts. But if they were, they probably have to sit down and do some merge conflict resolution. So another frequent use of a version control is to raise a bug, debug the bug probably with another engineer, and to close the bug. So let's go through that process using Git and GitHub. So after working at these 2 SPI devices, which is the LoRa radio and the e-ink, I realized that there was some SPI conflict, like both of them could not work together. And I had no way of knowing why this was happening, but I have a suspicion it's something to do with the clock pin. So in this case, what I'm going to do is go to the issue and raise a new issue, SPI conflict, and give some description. The LoRa and e-ink modules are not working together, and submit new issue. Maybe, label it as bug. And there you have it. We have a bug number 1 or issue number 1. So well, it seems like I have been able to debug it with a fellow engineer, and it seems we need to add a pull down resistor of 1K. So after I annotate them and make sure my entire electrical rules check is passing, I'm gonna check the git status, and yep, I have changed the schematic. And why don't we git add and git commit? And in this case, we will say fix, add a pull down resistor to solve the SPI conflict. Now GitHub has a cool feature where we can actually close the issue on GitHub by using just close and the issue number. Of course, instead of using close, we can also use other keywords. And another cool feature of the commit message is that we can add a co-author's name in this case. So I am going to do just that and add in Chinmay's name, who also helped me debug it. And let's do git push. watch what happens to GitHub issue. It gets immediately closed automatically. So let's go back to the main page of the GitHub repository. Here you will see that even the collaborator's name has been automatically added. All right, the next cool feature about Git branching is this concept of pull request, which happens on GitHub. It also uses the concept of branch. So let's say this time the firmware engineer will have to integrate in the firmware both the LoRa and the e-ink. So we'll create a branch called integrate LoRa and e-ink. And let's git check out to that branch name. So for now, the firmware only has a couple of folders. Let's add in the e-ink code. And there you see, after adding the e-ink code, we will see some visual indications that some code has been added, if of course our text editor has been configured to do so. And well, it looks like the firmware engineer is pretty happy. Just check the git status. Yep, all the firmware code has been added. Guess what? I do not want to add in this text editor. So I'll have to go here in my gitignore and add text editor. Maybe the entire folder of VS Code. So you see, it's always good to do git status. So let me add and then git commit. So it's a feature, add e-ink in firmware. Now I do want some discussion on this branch. So what I can do is I can push this branch to GitHub. So I can do git push origin and then this branch name. So now when I go to the Git repository, you will immediately see that a new branch has been detected and it will say compare and create a pull request. So yep, I am going to create a pull request and then say new feature. Now of course we can add reviewers and label them properly. But you know, another firmware engineer comes in and say, hey, refactor the code into smaller readable files. So this is where you can pretend a lot of the discussions will be going on. So what the firmware engineer will do is come back to the laptop, to the local repository on the laptop, and will try to refactor the code. And magically, the code gets refactored and abstracted away to a completely different folder for LoRa and e-ink. So let's do a git status. Yep, I have refactored the firmware and let's commit it to the same branch. This time it will be a refactor, abstract LoRa and e-ink code into separate folders. And I can also once again push the same branch to GitHub. And on GitHub, you will immediately see that the pull request has been updated with the new commit. So you see the first commit, add e-ink in firmware, and then the second commit. So let's just pretend that, well, all the engineers are happy with this code. What we can do is we can do a merge pull request. And yep, confirm merge. It will merge to the master and we can immediately delete branch as well. So you see now on GitHub, the latest commit will be the merge pull request. Whereas, of course, on my local laptop, it will not be so. So what I have to do is git pull so that it will pull the latest version from GitHub. Git pull origin master. Right, so now when I look at the Git log, you will be able to see that this was what was happening in the pull request, whereas this is what was happening locally. And if you compare the latest SHA-1, which is 4EEC, it is exactly the same as the latest on GitHub. So hey, among the pull requests, we completely discussed it, the feature on GitHub, and we also merged it with master. So another key advantage of using a version control such as Git is that we can fire off certain automated tasks at the point of certain execution. For example, with Git hooks, we can do certain tasks before, say, committing, pushing, or various other stages. A Git repository, a folder, will usually have this folder called .git. Let's open this up in our text editor. And we looked into other folders, but this time let's look into the folder called hooks. And here there are a lot of sample scripts. So what we will use is, let's say, a pre-commit script so that just before committing, the Git committing, it will check for certain stuff. As an example, let's install this library called Git secrets. It is pretty handy in the sense that it will look for some patterns in our code and will raise some alerts if possible. So for example, let's say in my firmware, I have a password and I erroneously did put in the password, the actual password. So in this case, I will create a new hook, a git hook, which is a pre-commit, and let me change the permission. And inside the pre-commit hook, it will simply do a git secret scan of the code. Now I will also need to edit the git config file, and here I will add in certain patterns. For example, through the regex, it will only say that the allowed pattern is secret, whether it's password or say Wi-Fi SSID. If it is any other characters, it will not allow us to commit the code. And then let's try to commit it, add password, which is something we should absolutely not do. It will say error matched one or more prohibited patterns. So now let's come and change it to secret, which is an allowed pattern. Will I be able to now add it? Password secret. Maybe I should add a comment and say replace secret with your password. And now it will be added. With this, I can safely git push to a remote repository. All right, so the last Git feature is tags. And well, who here has committed the Gerber files or even say some of the firmware build files such as ELF or bin file into our Git repository? Well, I used to be the one who did that. I'm totally guilty of it. But of course, if that is part of the team process to commit the file changes immediately with each of the changes in schematic or code, that is fine, but in this case it is not. So let's have a look at it. With Git tags, we can also create releases on GitHub to share the generated files and make a clear reference to the tree of the entire project. All right, so let's just pretend that for my schematic, I magically have the layout right now. And in order to create the Gerber files, well, first let's go and look at the file structure. So here with Git status, I of course have the schematic change, a PCB file has been created, and of course the footprint library table has also been updated because I acquired some footprint from the library. So now if you want to create Gerber file, it will have an output directory, Gerbers, and let's plot it. And let's also generate the drill files as according to the manufacturer's specifications. And now when we do a Git status, we will see that an extra folder of Gerbers have been created. And if I list the Gerber folder, you will see the familiar files of .gbr and drill files, which will typically go off to the manufacturer. So let's just pretend for a while that these are the files we will be sending to the manufacturer. So the first thing we will do is inside the gitignore, we will create a new section called generated files. And here we can safely ignore all the GBR files and also all the DRL files. And once we do that, when we do git status, you will see those files are not included. Well, let me include the Gerber folder as well. All right, git status. Yup, only the layout file, the schematic file, and the footprint library table file. Let's go inside the firmware and let's also build the firmware file. And I have put the output to be in the folder called build. And now when we do a git status, we will see this build folder as well, which will typically include the bin folder, the elf folder, and these are also the files that I do not want to commit. I will go to gitignore and add in the bin file, elf file, maybe zip as well later on, .map, and the build folder. One final time, git status. Am I all certain that these are the files that I want to commit? And yes, I'm very sure that this is exactly the snapshot of the entire project that I want to send to the PCB manufacturer. So let me create the git commit and say integrate LoRa and e-ink in PCB and firmware, and git push to GitHub. So of course, when I see it via the folder directory, we will see the build file for the firmware, and for the hardware also we will see the entire Gerber files. But in the GitHub repository, which is remote, we will not see the build folder here inside firmware, and neither will we see the hardware. Now here's the cool thing with git tags. So let's say we are certain that this is the commit. The last commit is the one that we will send to the PCB manufacturer. We can create a git tag version 1.0.0 with a little comment. So I'm gonna git push --tags to ensure that even this tag is pushed to GitHub. And now under here, under tags, we should be able to see version 1.0.0. And here we can create a new release and say v1.0.0. Yep, it will immediately prompt the current version. So we'll say v1.0.0 firmware and Gerbers. So now what we can do inside hardware, I'm going to create a zip folder. Let's compress everything. And I can upload the Gerber files in the zip folder. And I can also upload the build folder in zip format for the firmware. So let's publish the release. And yep, here you will be able to see both the zip folder for the Gerbers as well as the build folder for the firmware. And if you click version 1, it should be able to go to the exact tree for the entire code repository for which the Gerber and the build files were created. So I find this a lot cleaner. Instead of committing the Gerber files and the bin files into my code repository, I can just add it as a release. The last point that I want to touch is something about what these version numbers mean, especially like let's say I put version 1.0.0 and then the next one is version 1.1.1. What do these changes mean? Well, in the software world, there's something called semantic versioning, so that there is a standardized way of knowing what these version numbers mean. And semantic versioning states that the three numbers mean major, minor, and a patch. The major version means that there is an incompatible change. The minor version are just some additions, and the patch are some backward compatible bug fixes. While this is great for software, I'm still not really sure how to use it for hardware. Now, I found this blog post and some other write-ups on the internet, and I think they are generally in the direction of what the software world is also trying to do. For example, the major version in this case are some incompatible changes, for example, different board size, maybe mounting holes, and a minor version could be like a new feature, new component, and a patch could mean a small fix. But really, in the case of hardware, even if it is a small fix, does it mean that it will not become a major incompatible change? Well, I'm not really sure about that. Well, I have no answers to what the semantic versioning for hardware should mean, but I'm pretty excited about the concept of semantic versioning so that in the hardware world, when these numbers change, it might mean something in general. So that is exactly how I use Git daily in my hardware projects. For those of you who also use Git and come from the software world, once again, will realize that the tools are a little bit peculiar, a little bit awkward. It's trying to get there, and I can see a lot of efforts that are being put to kind of emulate what we have in the software world and bring in some of the cool features into the hardware development cycle. And that is why, seriously, a huge thanks to the developers, say KiCad or even Altium Designer, Particle, Adafruit, SparkFun, whoever, wherever you are, a huge thanks for building these tools that we can take in some of the good stuff from the software world and bring it to the hardware world to automate it, to check it, and hopefully these tools will become even better as we continue to use it. So I would love to know your tips and tricks on using Git if you have already used it. If not, do you have other ideas on how we should use Git for hardware development? And so thanks for watching this video and see you in the next one.